All right, hello everyone. I'm here today to talk about functional programming in education. I'll look at how it has been used, and I will talk about how I think it could be used. So let's get right into it. I'd like to sort of scope the talk to tertiary education, so something like university. And in particular, I really want to talk about that first semester programming subject called like Introduction to Programming or Programming 1 or something like this, right? It's the university subject that's meant to take people who don't know anything about computer programming and teach them how to write computer programs, okay? So I'm really interested in this subject and how we can teach it. One of the key questions we have to ask ourselves if we were to, say, design a curriculum for this subject is, which language are we going to teach people? In order to teach people programming, we will have to teach them some particular language for them to program in. And I argue that which language you choose actually has an enormous influence on the kind of course that you can create. So this is a Hello World program written in Java, and you'll notice there's an enormous number of constructs in this. So to actually understand what this code says, we need to know about things like classes, static methods, access modifiers, and so on, just to write Hello World. Okay, so I think a big part of that first programming subject is kind of dispelling the notion that computers are somehow magic or I don't have any control over the machine. And I think it would be really crushing if you got to the end of your first programming subject at university and you still didn't understand the first program you wrote, okay? So I really hope this convinces you that I'm not just bike shedding over my favorite language or your favorite language, but there's like a crucial difference depending on which language we pick. So one aspect of this is that there's a lot of syntax to the Java language. And there's this funny sort of thing that happens where quite often the structure of the subject, the sort of curriculum, will closely follow the syntactic structure of the language being taught. Okay, this has been referred to as the tyranny of syntax, but it'll be like, oh, in week 3 we do if statements, and in week 4 we do while loops. Okay, and I think that I mean, this might be a good way to structure a course, but I think it has a dangerous risk that comes with it, that the student might believe that what they're really learning is a while loop. You're not learning a while loop, you're learning how to solve problems with iteration, okay? And a while loop is a vehicle that will let you do that, okay? So it's very important not to confuse these things, and I worry that a course so closely structured around the syntax of the language can lead to this kind of conflation of concepts. And so I'd like to talk about a book called Structure and Interpretation of Computer Programs, or SICP, that was released in 1985 at MIT. And they managed to overcome completely the tyranny of syntax because they chose to teach introductory programming in Scheme. Scheme is a dialect of Lisp, and Lisp is infamous for having almost no syntax. The only syntax in Lisp is the S expression, and there are some special forms, such as define or if, which slightly change how the S expression behaves. But that's it. That's all we've got. Okay? And so in the very first lecture, they teach you how to define a procedure. They teach you how to use a conditional, like in this case an if statement. And they teach you iteration by means of recursion. So in the first lecture, they're able to show you a factorial function and do something kind of non-trivial, which I think is really cool. And they're only able to do this because there's very little syntax involved. So another advantage of using Scheme is that we can use the substitution model of evaluation. We can teach this to students. Oh, yes, Phil.
We teach factorial in the first Haskell lecture.
You're spoiling the rest of my talk, Phil. And so we have the, so we can use the substitution model of evaluation, where if we want to evaluate an expression that makes a function call, like sum of squares 3 and 4, we can replace the function call with the function body, but with the formal parameters replaced by the actual parameters. We can do this again for any other function calls, and we can evaluate the arithmetic as we normally would. Okay, and so we're able to proceed through this program and understand its evaluation as it goes. And we can visualize it in this way. We can get students to write it down. And so if they're having trouble understanding how a program executes, we can sit down and say, all right, let's substitute this out, let's figure it out. And this is an incredible model by which to do that. Compared to, say, an imperative model where you sort of say, all right, create a box in your mind for every variable, and then we're going to get into the loop, and we're going to figure out whether the loop condition is still true. That's a much harder model. In fact, later in SICP, they introduce assignment, and then they have to teach you a much more difficult mental model than the substitution model, and they generally spend a lot of time apologizing for it. So a substitution model is a really powerful teaching tool, I think. And what's incredible about it is, even in this first lecture, the substitution model actually gives us a sort of really informal, albeit, but an actual notion of complexity. We could look at the shape of the substitution model evaluation of this expression, and we can say, as we get further and further in, we go further and further out to the right. Do you see how it gets wider and then it comes back in? This roughly corresponds to the space usage of the program. Okay, the further to the right we go, the more space we're using. And the further down the page we go, the more time we're using. This is very informal, but this just gets students right from the beginning thinking about computers as having resources, like time and space are things I will have to think about. They cover complexity in a more formal way later, but just getting this idea across really early, I think, is helpful. And they're able to cover an incredible breadth of content throughout the rest of the book. So they talk about symbolic computation with quotations and quasi-quotations and things. We define interpreters. We implement logic programming by modifying scheme itself. And it's just, I think of the book as like this tasting plate of computer science. It's just sort of got a little bit of everything, okay? But it's not all smiles and sunshine. So in 1987, Professor Phil Wadler made some comments about how we ought to use Haskell or something like it, as he did. So Wadler argued that the content of SICP, please correct me if I say anything wrong, Phil, but
I will.
Yeah. The content of SICP is excellent, but it would be easier to teach if we used a strongly statically typed lazy functional programming language. Now, at the time, they were talking about KRC and Miranda. Those were the sort of popular strongly statically typed lazy functional programming languages at the time, but I'm going to talk about Haskell because that's the popular strongly statically typed lazy functional programming language today for some definition of popular. And there are some real advantages to this. So we have things like data types. So this is a data type definition for a list, and it says a list is either nil or it's cons, right? And if it's cons, it's got two things, an A and a list of A's. Okay, so we actually get to look at what the definition of a list is. In structure and interpretation, there's a paragraph with effectively a comment that says a list is a chain of constants that ends in the empty list, right? But you never actually get that as like a construct in your language. It's sort of in this meta sort of comment-based language. But the really incredible thing about this is that because these languages, or I'm going to talk about Haskell, but Phil was talking about Miranda. But because languages like Haskell have pattern matching, this definition actually tells us how we work with the data. So here's a function that, given a list of numbers, will compute their sum. And this one's in scheme, and it basically says this. We get our items. We ask, are you the empty list? And if the answer is yes, the sum is 0. If the answer is no, we pull the head out and we pull the tail out. We take the sum of the tail and we add those two things. Okay? Writing this requires remembering an awful lot about the structure of lists and reading it as well. So we ask with a predicate, are you the empty list? And then if that predicate returns false, we just start pulling out the head and the tail, right? What if it wasn't a list? Nothing says it wasn't a list, but also, like, the definition of list isn't really sort of talked about on this slide very much. Like, we're in the else case, we have to go in for a while and then say, oh, there's the car, and there's the coda. That means head and tail in Lisp. But what's beautiful about pattern matching is we can see these are the only two cases that a list can be. Okay? It's either nil or it's cons, and if it's cons, it has two things in it. When I'm programming, let alone someone who's just learning how to program for the first time, but when I'm programming, I'm always worried that I'm going to miss a constructor. Like, oh, in my pattern match, did I get all the constructors? Or when I pulled the stuff out of the constructor, did I pull out everything that was in there? And the great thing about strongly statically typed languages is they will tell me, right? If I missed a case in my pattern match, here's the Haskell. If I miss a case in my pattern match, it will tell me. Or if I forget to pull everything out of the list, it will tell me. Okay, so you get this kind of helpful feedback as you program due to the strong static type system, whereas the feedback is not always so good in Lisp, particularly if you pass a thing that isn't a list. It will try to take the head of it, and it won't go so well. The other excellent thing about strongly statically typed lazy functional programming languages is that they're lazy. All right? So there's a bit in SICP where they say, they sort of define normal order evaluation and applicative order evaluation, and then they say, and scheme uses applicative order evaluation, and then they have a really mean exercise where they define if as a function. And the exercise is, why doesn't that work? Okay, and Wadler in his paper commented that most of the students don't understand why. I think you need to really work with both sort of normal order languages and applicative order languages to kind of be able to build a mental model such that this question makes any sense. The reason it doesn't work, by the way, is because with if as a function, we evaluate both the then clause and the else clause before we even get around to looking at the if to make a decision between them. So if we write a recursive function using this if, then it will always run forever. When we're using a language with lazy evaluation, this quite simply isn't a problem. You can write if as a function. You may even choose to teach it that way. All right? So rather than having a really mean exercise that says you should think really carefully about the order things are evaluated, just don't. Yeah, so laziness is really cool for this reason. So this gets back to what I was talking about with the substitution model. So the substitution model actually can lead you to lies if you're not extremely careful, unless your language is lazy, in which case it will always give you the right thing. It will always do what you expect. Substitution properly works when you're in a lazy language. Wadler wasn't the only one to suggest improvements to SICP. There were also a group of academics who wrote a paper rather cheekily titled Structure and Interpretation of the Computer Science Curriculum. And this was way later in the 2000s, or 2001, I think. And they said, here's what we think a good introductory computing course would be like. Here's what it would teach, here's how it would teach it. And then they analyze SICP according to this framework. And they have some problems. So one of the problems is nearly all the examples in SICP are drawn from extremely technical domains. So I said we learn sort of symbolic computation with quotation. We do that by writing a derivative program. And I personally would like to be able to teach programming to people who don't know calculus at all. I think that's a reasonable goal. Another example of a problem domain that is sort of this digital circuit design. Now, in all fairness, structure and interpretation in 1985 was mostly being taught to electrical engineering students at MIT, right? These people were across calculus and probably digital circuit design and all these sorts of things. So in the context in which the book was published, this isn't a problem. But in the context I'm interested in, it is. But their more fundamental criticism of SICP, and in this case, they're actually quoting someone else. They're quoting Jackson and Chapin, I suppose the pronunciation is, I hope, who late in the course's life taught SICP. And they sort of said, we have come to the viewpoint that the first course should focus really on basic notions of modularity, specification, and data abstraction, and not lots of interesting little bits of computer science. Okay, and I think this is a really good paper if you're interested in how things are taught. And so they actually sort of said, we'll write our own purple programming textbook. And so they released How to Design Programs. They actually released it before they wrote the paper, but the narrative of the talk doesn't work if I present it in that way. So they wrote their own purple programming textbook, and I think it's a really excellent textbook. So they still used Scheme, and they used Scheme in their own little IDE. So this is an IDE that sort of they tell you to pick up in the textbook. And the IDE is very simple. It's just got this code window, and then it's got this little REPL window, which encourages a playful interactive style of writing programs. The other really excellent thing they do is they use a staged approach to Scheme, where as you progress through the book, more and more language constructs and library functions become available to you. Okay, so as you grow, the language grows with you, and you've always got just enough stuff. And the cool thing about that as well, even cooler, is as you grow and the language grows with you, the IDE grows with you. More and more functionality from the IDE is unlocked as you progress. So when they introduce assignment in the most advanced version of the language, originally you have this little substitution evaluator where you can evaluate your expressions step by step, forwards and backwards, and just kind of watch how they work. Okay, it's really great. Then once they introduce variable assignment right at the end of the course, you can't do that anymore. It doesn't work. So they replace it with this much more complicated debugger that will tell you about the stack and the state of all your variables. Okay, and so you use this debugger instead. And so as you learn more, you kind of get tools that are appropriate to what you're learning. They also seem to agree with Wadler somewhat on types. In their version of Scheme, even in the most advanced form of it, the second argument to const must be a list. And you get a type error if you don't put a list there. So this is totally against every other Scheme implementation on the planet, I think. But I think it's better. I think if you're not going to teach a strongly statically typed programming language, well, I suppose the next best thing might be a strongly dynamically typed programming language. They also have the best exercises I've ever seen. Things like look up the documentation. I'd just like to remind everyone, this is a course about teaching programming, right? So read the docs. This is usually not covered. They also have these other excellent exercises, like pass something of the wrong type to the function and see what happens. Okay? That's an excellent exercise, because we need to learn to work with error messages. Okay? They're going to occur, and we need to be able to read them. I'd prefer them to be at compile time, but we need to be able to work with error messages to kind of get towards a solution. And I think having an exercise like this sort of says, don't be afraid of error messages. In fact, try to sort of probe the code and figure out what the error messages might be. They also have these things, you don't have to read all this, and I won't read it to you, but they also have these things called design recipes, where they teach you, they sort of have this step-by-step process for things like how to write a function, or like how to write a batch program or an interactive program. They actually teach you this kind of thing. It'll be like step 1, write down what the function should do. Step 2, come up with some examples. Step 3, look at the input data for the function, and then use the template that's shaped like that input data. It would be a pattern match in a different language. And then when you're done writing the function, turn the examples you came up with into executable tests. Okay, so they sort of talk about the full lifetime of writing a function, from figuring out what the function should do through to actually testing it at the end. This is really good. We should be doing this when we teach programming. I think they make a comment in their paper, something along the lines of, in most introductory programming courses, they will teach you a programming language and expect you yourself to figure out how to actually go about programming. But these guys are just like, why don't we teach that bit? That's like the actually important bit. And I think they do a great job of that. So structure and interpretation of computer programs is an incredible starting point. Wadler suggested some improvements. The How to Design Programs people suggested some improvements in a completely different direction. I want to know what's up here. So I'd like to see a course that has the kind of focus on foundational problem-solving techniques that How to Design Programs had, but all the advantages of strongly statically typed lazy functional programming languages that Wadler talked about. I think that would be the best programming introduction ever. So I'd like to use something like Haskell, but there are some problems with that. For example, if I type 3 plus false, what I want the student to see is an error message that says, that can't be done because Booleans are not numbers. Here's the error message. Now, GHC has impeccable, excellent error messages. Here's the error message GHC gives me, which says, no instance for num_bool. Now, that does say you can't do that because Booleans aren't numbers. But it says it in a really, really Haskell-y way. Like, I need to know type classes to even attempt to read this error message. But also, if I try to view it, if I sort of put myself into a beginner student mindset and I've never learned programming before, when I see this error message that says no instance for num bool, I think to myself like, oh, no instance. Have I forgot to import something? Let me check the lecture notes, okay? And I go off and get distracted with something completely else. So I'd really like to have an error message that says you can't do that because Booleans aren't numbers. And this is just one example, but of a bigger problem. Thankfully, as of GHC 8, GHC has the capacity for custom type error messages. So I can attach a type error message pretty much wherever I like. And so if I say 3 plus false, I can make it have an error message that says Booleans are not numbers, so we cannot add them. So if I were going to teach someone programming, I would teach them Haskell, but it would be a version of Haskell that was full of custom type error messages for things like this. And whenever a student made a new mistake that I hadn't even considered, I would then be able to add that. I would also use, because in GHC we can use no implicit prelude and then provide our own prelude, I would give a staged introduction to Haskell by means of a series of preludes. Okay, so you'd start with a prelude that's very simple, like you can only add integers. Okay, and then as you learn more about Haskell, you'd get access to more and more library functions, and they would become more polymorphic and things like this. And it would all be full of custom type error messages. All right, so I'd like to end the talk with a sort of brief personal anecdote. That's sort of my attempt to come up with such a course. So this anecdote, when I learned to program, I learned at university in the first year, first semester course. And it was the best educational experience I've ever received, probably by far. All the lectures were incredibly well presented, well put together. The ideas were clear. The tutorial exercises were sort of well put together to be challenging but achievable and very well written out, so there's no ambiguity what you were being asked to do. I was just blown away that education could be done so well. And I think that course really sort of changed my life. And we got to the end of the course, and in the last lecture, the lecturer said, oh yeah, by the way, I would have rather taught you my favorite programming language, Haskell. It's very different. It doesn't even have loops. And I said, what? I've just spent a whole semester learning how to program, and I solved every problem with a loop. Loops are how you program. How could you program without any loops? And so then I went and had to go and learn Haskell, didn't I? But I would have liked to have seen the world where that lecturer did teach Haskell. Like he wasn't even operating at his full power level with the course that changed my life, right? I want to know the course I missed out on, okay? And today I hope I've gestured in that direction. That's the end of the talk.
Thank you, George.